remember those sets that we defined in the previous lecture? They were both collections of subsets of the unit interval 0, 1, right? This was the set of elementary sets, and this was the set of Jordan measurable sets. Just to remind you, the elementary sets were the finite unions of intervals, and all kinds of intervals, and the Jordan measurable sets were those ones that could be approximated from above and below by elementary sets in such a way that the measures of the elementary sets limited to something that agrees from both above and below. Yes, maybe I'll Jordan measurable sets. So this one is actually an algebra of sets on this. So the elementary sets form an algebra of sets. We have, I think we discussed that, the finite unions of elementary sets are elementary sets. Finite intersections, complements. If you take the complement of a finite union of intervals, then you get a finite union of intervals, right? This one is also an algebra of, let me just be lazy. This one, the set of Jordan measurable sets, is also an algebra of sets on here. That one I think we didn't quite show, but a component of it is part of your homework. One of your homework problems is to show, so let's go back and see what do we need to show exactly over here. This is my more compact definition. Let's see, for an algebra of sets on X, I need to show first that the whole set is in there, and is the entire unit interval 0, 1, is that a Jordan measurable set? Yes, in fact, all the elementary sets are very trivially Jordan measurable, and it's an elementary set, right? It's an interval. And two, if I take two things that are Jordan measurable and I union them, is that Jordan measurable? That's actually on your homework, so I'll leave that for your homework. And the third thing, if you take a Jordan measurable set and then complement it within the unit interval, then is that Jordan measurable? So let's just look at that. So suppose A is Jordan measurable. So just to spell things out clearly in words, what I'm saying is that A is a subset of 0, 1, and A is Jordan measurable. Then there are families of sets, sequences of elementary sets. One sequence that builds up to A, so nested and union is A, and another sequence that comes down onto A, nested in the other direction, and intersection is A, such that AN, BN are sequences in this collection of Jordan measurable sets. Sorry, such that they're in this collection of elementary sets. And also such that when you take the Jordan measures of these complements, then that is a sequence that goes to 0. So all that so far is coming from the definition of what it means to be Jordan measurable. Then I want to prove that the complement of A is Jordan measurable. So that's the complement in the full space, which is the unit interval here. I want to prove that this is Jordan measurable. And you know, it's going to take me forever to write this a bunch of times, so let me just temporarily use this notation of using an over bar for a complement. Don't do this unless you introduce it using a sentence like what I'm about to write, something like, let us write S bar for this, for any subset S of the unit interval. Okay, so now what I want to prove is that A bar, I should write that after I introduce the notation. So want to prove that A bar is in there. So a good first thought is maybe the complements of the ANs and the BNs are going to be useful. We already believe that the collection of elementary sets is closed under complement. And we're trying to show that the collection of Jordan measurable sets is closed under complement. So we already believe that if we complement the ANs and the BNs, then we get elementary sets. So maybe their complements will be helpful. So will AN bar perhaps be helpful? Let's see. So what we know about the ANs is that A1 is contained in A2, is contained, etc. They're all contained in A, right? And their union, the union of the ANs, is equal to A. That's what it means when we say the ANs build up to A. So this notation is a compact way of saying the information that I'm writing here. Now, what happens if I take complements? So if I complement everything, then the inclusions flip around. So they become like that. So it's a nested sequence going the other way. And now, instead of being sets inside of A, I'm looking at sets that contain A complement. And if I complement both sides of this, well, then this is true. I just complemented both sides. But according to De Morgan's law, I can distribute the complement inside and replace the union with an intersection. So like this. So this is what happens when I complement everything in the original picture. And so what does that mean? It means that the AN bars form a sequence of sets which is coming down onto A, limiting down to A, or however you want to pronounce this. And notice that the AN bars are all elementary sets, since they're complements of elementary sets. And you can do the same thing with the BNs. So you similarly get that the BN bars are going to build up to A, and the BN bars are complements of elementary sets, so they're elementary sets. And it remains, so if we can show that the Jordan measure of the difference of these two elementary sets goes to 0, then we are done. Then, I'm sorry, this is bar here. That's the whole point. We're trying to show A bar is Jordan measurable, right? So if we can show this, then we will have A bar is Jordan measurable, which is what we want. Okay, so let's think about these kind of complements, these relative complements, Bn bar minus An bar. So everything in sight is inside the unit interval, right? And these bars just stand for unit interval minus the set. All points that we're talking about here are in the unit interval. So this would be the set of things that are in Bn bar and not in An bar. So the set of things that are not in Bn and not in An. So in other words, the set of things that are not in Bn and in An. So this would be An set minus Bn. Which is not so useful of a thing to look at, actually, because these are all empty sets. I got this backwards here. What I want to show is that, yeah, I got this backwards. The AN bars are coming down onto A, so they're like their measures will be overestimates of the size of A bar, and the BN bars are building up to A bar, so they will be underestimates. And what I want to look at here, according to the definition of Jordan measurable, is the AN bars minus the BN bars. So that was pretty sloppy of me to look at that. Okay, so over here, this is the set of things not in AN and not in BN. So in BN and not in AN. Okay, so then this sequence of numbers is actually the same as this sequence of numbers. It is that sequence, and it goes to 0. So that proves that the set of Jordan measurable sets is closed under complements. If you also include with that what is on your homework, which is one of the things on your homework, which is proving that it's closed under union, then you will know that this is an algebra of sets on... this is another line that doesn't make sense. Wow. It's an algebra of sets on the unit interval. It's an algebra of sets on the unit interval. Okay. However, it's not a sigma algebra on the unit interval. So remember, the difference between an algebra of sets and a sigma algebra is that sigma algebra needs to be closed not only under finite union, but countable union. And remember, we noticed last time that this set is not Jordan measurable. However, this set is a countable union, right? The rational points in the unit interval, there are only countably many of those. So this is a countable union of singleton sets, all of which are Jordan measurable. So this could be written as the union of, let's say, R, for all the R's in singleton R, for all the R's in there. So just write it as a union of singleton sets. These singleton sets are definitely Jordan measurable because they're elementary sets, because they are, let me frame it this way, they are intervals in this sense. So this is a countable union of Jordan measurable sets, but it is not Jordan measurable. So the set of Jordan measurable sets fails to be a sigma algebra. So what are some examples of things that succeed at being sigma algebras? Well, here's some trivial ones. One would be the set consisting of, so let X be any set. Then here are two immediate sigma algebras that we can just write down right away. One consisting of only the two things that it has to contain, and one consisting of literally everything. So these are like the two extremes. Those are definitely sigma algebras. And any other sigma algebra is going to be somewhere between these two extremes. So if you want to check that these are sigma algebras, you have to check closure under complements. Yep. Closure under countable unions. Yeah, there's not much you can get by unioning things in here, right? And this just contains everything. So it's going to be closed under complements and countable unions. Okay, but you probably want a more interesting example of a sigma algebra, right? Well, we're going to start by looking at how you can, what happens when you try to generate a sigma algebra starting from a generating set. And we'll see what we can say about that.